Hello friends, you are watching ERUDIRE Plus, the professional CAD/CAM solution provider. Let's get started.
Hello viewers, today I'm going to show a basic finite element problem using ANSYS mechanical APDL, and that to be validated using theoretical calculations. Let us see the problem. Problem is, obtain the first 10 natural frequencies of the fixed beam shown in figure and compare them with the theoretical values. Also plot the mode shapes, and provided values are actually modulus of elasticity equal to 2.068 into 10 to the power 11 Newton per meter square, Poisson's ratio equal to 0.3, and density of the material equal to 7830 kg per meter cube. You can see the beam, this is fixed at both ends. The length of the beam is 1 meter, and you can see the cross sectional area. It is a square cross section of 1 centimeter by 1 centimeter, that is equal to 0.01 meter by 0.01 meter, right? So without wasting time, let us start our finite element analysis using ANSYS mechanical APDL. Right? First of all, we need to save this work in a specific folder. For that, let us start with file and change directory. We can change the directory to any location. Next to that, we need to change title of this one. So file, change title, and we can change as per our requirement. Let us make this one as FU1. Okay, then whatever we have written, the file name is not visible, that to be seen from here. If we click plot replot, that will be visible. Plot replot, so you can see that file name at the lower left corner. Next to that, we need to start from preferences. You know that in finite element analysis there are 3 different steps: pre-processing, processing, and post-processing. So first of all, we need to start with pre-processing. It is consisting of a lot of steps. First of all, we can start with preferences, and it is a structural analysis. So we need to define the elements. It will be coming from pre-processors. Element type, add, edit, delete. Nothing is defined, so we need to add some elements. Add. We're considering beam with 3D finite strain. Okay, and from options we can select element behavior as cubic only. Next to that, we need to add material properties, material models, structural, linear, elastic, isotropic. Isotropic means material property remains same in all directions, and modulus of elasticity equal to 2.068 into 10 to the 11, 2.068 E11, and Poisson's ratio equal to 0.3. Okay, next to that, we need to provide our density. Density equal to 7830 kg per meter cube. Done. Next to that, we need to provide sections, because it is a beam with both the ends fixed, and it is having cross sectional area of 0.1 meter by 0.1 meter. It is a square cross section, so that cross section should be provided from here itself. Section, beam, common sections, and it is a square cross section, so we can provide breadth and height of this one as 0.01 meter breadth and height equal to 0.01 meter. Provided. We can preview this one also. Let us see. This is the cross sectional area of this beam. Okay, done. Next to that, you need to start our modeling, and modeling will be started from here. While modeling, we can do one thing. We can create nodes, or we can create key points. Anything can be done. If we are creating nodes, in that case meshing is not required, but if we create key points, in that case meshing will be required. In this case, we'll create only key points. So starting with key points in active coordinate system. So the location is needed. We know that length of the beam is equal to 1 meter, so we'll create 2 key points. One key point will be produced at the origin, and another will be produced at a distance of 1 meter from extreme left hand side. So it is asking the location of key point. By default it will take origin. So if you are not providing any value to this one, by default it will take origin. Apply. So first key point is made, second key point will be produced at a distance of 1 meter. One is provided. Okay, so we have produced two different key points, and the key points are having at a distance of 1 meter. Next to that, we need to provide lines. It will be straight line. We can join these 2 points. Done. Right, now the thing is, we need to mesh it to make more numbers of elements. More the nodes, more will be the elements. So our plan will be to make this line into 10 numbers of divisions. So 10 elements will be there, and it will be having total 11 numbers of nodes, because in between each element 2 nodes will be there, right? So starting with meshing, size controls, manual size, lines. Let us select the lines. Okay, now number of elemental divisions are asking. Let us provide total numbers of elemental division equal to 10. That means total 10 numbers of elements we are producing, and in between them total 11 numbers of nodes will be created, right? 10. Okay, you can see 10 numbers of elements are produced. Now that to be meshed. So starting with mesh and lines, pick all, meshing is done. You can see that nodes also from here that can be viewed. Plot nodes, these are the different nodes. You can see total 11 numbers of nodes are there, and in between 2 nodes 1 element will be there. So it is having total 10 elements and 11 nodes. Let us plot elements again. Next to that, we need to start our solution. Analysis type, new analysis. It is a modal analysis, because our task will be to produce 10 numbers of mode shapes, and also that to be plotted. We're starting with modal analysis and analysis options. Different options are available. By default it is taking block Lancos, but we'll take PCG Lancos for this analysis. And numbers of modes to extract equal to 10, and numbers of modes to expand also we are considering 10. Okay, and options for PCG Lancos modal analysis, we're considering default setup for this one. Now we need to apply loads, right? That will be coming from apply structural displacement on key points, right? We're having total 11 nodes and 10 elements, and at the extreme left hand side and right hand side we are having 2 key points that will be fixed, because it is a fixed beam. So we're applying structural displacement on node. Let us select first location and the extreme right hand side location. Okay, and all degrees of freedom will be having 0 displacement. By default it will take 0 value. We are not providing to this one. So the displacement of left hand side and right hand side will be completely restricted. So the boundary condition is applied. The beam is completely fixed, right? Done. Next to that, we need to run it. Solve current ls. Solution is done. Now you can see your results from general post processing. Let us see results from general post processing. First of all, see the 10 set of results from result summary. You can see that the first set is having frequency of 52.790. First and second both same. Similarly, third and fourth is also same. Third and fourth is 145.39. Similarly, fifth and sixth is equal to 284.68. Seventh and eighth is same. It is 469.89, and 9, 10 is also same. It is 700.77. These are the modal shapes. Now that we plotted, we want to plot these mode shapes, right? For that, we'll start from read results, first set, and we can plot it right now from plot results. Deform shape, we're going to see deform plus undeform. That means the change drawing and original drawing, we see both, right? So this is the first more shapes. As it is the results, we can save it from plot controls capture image, and we can save it by the name of more shape 1. We can name it ms1. Done. Close it. Let us see the next one. Read results, next set, plot results, deform shape, deform plus and deform. Okay, so it is coming back to the original position again. We'll go back to the next one. So read results, next set, plot results, deform shape, deform plus and deform. This is the next one. So this is the next mode shape, right? In this way you can go for checking all the different modes one by one, right? Let us see all these things. Read results, next set, plot results, deform shape, deform plus and deformed. This is the mode shape. This is actually fourth one. Next one again, read results, next set, plot results, deform plus and deformed. This is the fifth set. Again, read results, next set, plot results, deform shape, deform plus and deform. We can save all these things as these are the results, right? We can see the next one again. Read results, next set, plot results, deform shape, deform plus and deformed. This is the seventh one. Then read results, next set, plot results, deform shape, deform plus and deform. This is the eighth one. Then again the ninth one, it will be read results, next set, plot results, deform shape, deform plus and deform. This is the ninth one, right? The same way you can see all the things. This is the ninth one, and white one is the original drawing and blue one is the changed one. This is the actually you can see the frequency of beam, and you can see the amplitude at different locations. This amplitude also can be seen from list results, right? You can see it, list results, modal solution, and we want to see degree of freedom solution. I want to see displacement in y direction. That is the amplitude, right? So these are the amplitudes. You can see these are the values, and you can see a maximum displacement is occurring at node number 7. It is 1.5968, right? You can see here. You can save this one, file save as, and also we can save the result summary also. Result summary, you can save it. All results are saved, right? Now we can do one thing. We can see the animation of this one that can be viewed from here. Plot controls, animation, mode shape, and with default setup, let us see it. You can see how the beam is vibrating, and we can make it faster also. So this is the vibration of that fixed beam, right? Let us stop it and close it. And this is actually 2D. We can see it in a 3D format also. For seeing this one in 3D format, we need to start from plot controls, style, size and shape, and display of elements should be on. You can see this is the beam, right? Next to that, we need to validate our results using mathematical calculations or theoretical calculations. Before that, let us see the results, what we did before, what we got before. It is actually 52.79 is from ANSYS. Second one is 145.39. Third one is 284.68. Fourth one is 469.89, and the last one is 700.77. These are the frequencies, right? And these values to be obtained using theoretical calculations. Let us see this one. It is a beam fixed with both sides, and length of this one is 1 meter, and it is a square cross section of 0.01 meter by 0.01 meter. It is having modulus of elasticity equal to 2.068 10 to the 11 Newton per meter square. Poisson's ratio is 0.3 and density is equal to 7830 kg per meter cube, right? Now the thing is, if you want to have frequency of this one, you can see frequency is equal to 1 upon twice pi into angular velocity. And angular velocity also can be represented in a different term. Angular velocity equal to, for the first one it will be omega 1 22a divided by a square. Omega 2 for the second one it is 61.7 into a divided by a square, and for the third one omega 3 equal to 121a divided by a square. A is a term associated with modulus of elasticity, moment of inertia, cross-sectional area, and also density. So A equal to square root of EI by rho A. We are having all this data known. Modulus of elasticity is equal to 2.068 10 to the power 11. I is actually, it is a rectangular cross-section. I should be equal to B d cube by 12. B equal to 0.01. D is also 0.01 because it is having a square cross-section. So modulus of elasticity will be B d cube by 12. 0.1 into 0.1 cube divided by 12. Density equal to 7830 and cross-sectional area equal to 0.1 into 0.1. So by applying all these things, you can get the value of A, and that can be put in the equation of omega. So we'll get different values of omega 1, omega 2, and omega 3. And finally, from frequency, we'll get Fi equal to 1 upon twice pi into omega. So we'll get all these values. So these are the theoretical values obtained from these equations. So first case we got frequency 51.935, and from ANSYS we got 52.790, and in this case we got percentage error equal to 1.7%. Second case you can see frequency equal to 145.654, and from ANSYS we got 145.39, and we are getting percentage error equal to 0.04. It is very less. And third one we are getting theoretical frequency equal to 285.642 Hz, and ANSYS it is providing 284.68 Hz, and in this case we are getting the percentage error equal to 0.02%. In all these cases percentage error is within the limit. So the theoretical calculations were validated using ANSYS mechanical APDL, or we can say the reverse one. ANSYS mechanical APDL values were validated with theoretical calculations, right? So this is all about our analysis. This was a very simple analysis, and in this analysis we got 10 mode shapes of a fixed beam, and by the same time we compared their frequencies with the theoretical values. Thank you so much for watching this video. Thank you again. Bye. If you like this video, please subscribe and share, and if you have any kind of doubts, please write to me. Thank you so much for watching this video. Thank you again. Bye.